Hi everyone, welcome to the first video in the first unit on limits. You're taking notes in your composition notebook. The first thing you need to do is to put the title of the video, Finding Limits Graphically, and then write the objectives for the video in your notes. I'll be looking for those when I check them. Feel free to stop the video at any time so that you can take notes, draw diagrams, make conclusions, write question marks or stars wherever you need to so that these become your notes. As you recall, calculus is the mathematics of change and of infinity. It consists of the two major ideas, the tangent line problem, which is our derivatives, and the second is the area under a curve part, which is the integration part. But the fundamental concept under both of these and of all calculus is the idea of a limit. And some of you may have been introduced to a limit in your pre-calculus class, and some of you may not. So I want to talk about what is a limit and the limit process. And then we're also going to continue on finding limits from graphs. All right, so first you see I have a picture here of a phone book. I got my arrow working. Here's the phone book, right? So say you wanted to find the limit. The limit's a little bit like finding information in a book, right? If the stuff that I want to find is in the middle somewhere, then I could flip through the pages from one side and flip through the pages from the other side until I reach where that information is located. So the idea of a limit is that you're coming at it from one side and to the other, and you're seeing where that's located. Another way to think of it is this down here, and this is Zeno's paradox. And some of you have heard of Zeno's paradox, maybe not. There are many different ways of saying this one. This is the particular one says, if I am standing here and this is the wall, and the rule is that every time I move, I'm going to go half the distance from my position to the wall. So the first time I go half the distance, and then I go half again, and half again, and half again, and half again, and half again. And the question becomes, will I ever reach the wall? Well, yeah. I mean, my nose is going to hit the wall, right? So physically, I will hit the wall. Mathematically, however, will I hit the wall? So there's the paradox. So mathematically, no, you'll never reach the wall. And that's the idea of a limit, that you're taking infinitely smaller and smaller slices as you reach your destination, and you do it from one side and the other. So here's the definition of a limit. Be sure that you write this down. The definition says, if f of x, and this function in blue is the function f of x, if it becomes arbitrarily close to a unique number L for limit, as x approaches c from either side, then the limit of f of x as x approaches c is L. This is written as the limit as x approaches c of f of x equals the limit. All right, so what does this look like graphically? Well, here's my function, f of x. This is the x-axis, this is the y-axis. And somewhere here, I have an x value called c. So down here, because it's a continuous function, this point right here would be f of c, right? So this ordered pair would be c, f of c. Okay, function notation, we kind of have that. All right, so what this is saying is as x gets arbitrarily close, right, is as f of x becomes arbitrarily close to a number L as x approaches c from the left and x approaches c from the right, then the limit becomes that value. So as I'm getting closer, right, as I'm getting closer to c from the left, what is f of x doing? Well, it's getting close to here. And then as I approach c from the right, then f of x is going here. So this limit would be f of c, this f of c value. So here's a concrete example. All right, we have a line with a hole in it. and the whole is at where x is equal to 1. So say, for instance, we wanted to look at the limit of f of x as x approaches 1. I want to know what the limit is. All right, so here's my 1. So I'm going to follow the graph to here, and I'm going to follow the graph to here, and I'm going to look for f of x, right? And the f of x is 2. So the limit of this function as x approaches 1 is 2. But I can hear you saying, f of 1 does not exist. Doesn't matter. It doesn't matter that it doesn't exist there, because what you're looking at in a limit is you're coming from the left and from the right. You don't actually get there. Kind of like Zeno's paradox, right? You never hit the wall. So you're never actually getting to that value. Now, there are some graphs where it is defined, f of 1 is defined. The limit is the same. It doesn't matter what f of 1 is. Okay? So that's real important graphically. So here's another example. You can see here that this function is a piecewise function, but it's obviously not continuous. There's holes in the graph. There's also a discontinuity that we call a jump discontinuity. So everywhere that it is continuous, we know that the limit, like say for instance, I just picked this point right here, this x value, the limit as x approaches a half, is going to be an actual value. So that's not very interesting. So the interesting parts are the parts where it's discontinuous. So let's take a look at that. So let's say, what is the limit as x approaches 1 of my function f of x? All right. So I look here, and sometimes we call this the thumbs test. We come at it from the left, we come at it from the right, and the y value is at 1. Even though we know that f of 1, the point, the actual point, f of 1 is 2, but the limit is 1. All right, so let's jump over to the limit as x approaches 4 of f of x. All right, we know that f of 4 does not exist, right? Because there's a hole there. But the limit does exist because it's the same from the right and from the left. So we look here and it approaches from the left and it approaches from the right, and we know it is at 2. So the limit of that is 2. Now, let's look at the limit as x approaches 2 from the left, and let's look at the limit as x approaches 2 from the right. Okay, and so we have here, as it approaches from the left, it is 2. But as it approaches from the right, it's 3. So because these are different, they say that the limit as x approaches 2 of f of x does not exist, because they're different from the right and from the left. So once again, let's look at a couple of these. We're still looking at where the limit does not exist, because where the limit exists, it's a fairly simple thing to find. So looking at this first example, we can see clearly that the limit exists on this function all the way to here, and the limit exists on this part of the function all the way to here. The limit does not exist, right, where the limit from the left and the limit from the right are two different numbers. So the limit from the left exists, the limit from the right exists, but the limit from both right and left does not. Now, this next function is a very interesting function. This is the absolute value of x over x as the limit as x approaches 0. And if you look at this function, let's plot a couple of points here, right? So when x is negative 2, this would be negative 2, but the absolute value, so 2 over 2, which is, 2 over negative 2 would be negative 1, right? Then if I put a negative 1 in here, this would also be negative. But if I put in a positive 1 and a positive 2, then it becomes positive. So you kind of see it looks like this very interesting piecewise function, but f of 0 does not exist. Okay? So the limit as it approaches from the left is -1, and the limit as x approaches 0 from the right is 1. And so you can see that at 0, the limit does not exist. We're going to talk a lot more about this function because it's a real interesting function, and really the way to get it is you just need to know what it looks like. One other place where a limit will fail to exist is at an asymptote. All right, and you can see here these are both rational functions, and we have an asymptote here, vertical asymptote, right? There's also a horizontal one on both of these. These are both rational functions, but at the asymptote. So if you see here, all of these values here, all of this part of the graph, all of this, all of those have a limit. It's a continuous function. It's the same from the left as it is to the right. Perfect. Same here. Here, at the asymptote, you can see that as x approaches 0 from the left, f of x is going to infinity, negative infinity. As x approaches 0 from the right, y, or the f of x, is approaching positive infinity. If I were to put my thumbs on either side here, you would see that they do not come together, no limit at 0. Okay? But here, we also have as x approaches 0, here's the asymptote here, then f of x is approaching positive infinity. And here, as f of x is approaching positive infinity, they're going in the same direction. And we're going to talk about this later, but it still does not have a limit. But because they're both going in the same direction, sometimes they will say that the limit here is positive infinity. So the important thing to remember is that whatever is happening from the left and from the right has to be true for there to be a limit there. So I want you to go back, and now that you've taken your notes, I want you to write in key terms and key ideas in that margin of your notes where we've done that before, so that you can go back and study some of these things. The stuff that we have in class, we're going to go back over and look at these, but if you'll get these underlying concepts and study as you go along, it will make understanding these things very easy. So get your notes done. I'm going to check them, and we'll see you in class.